This is the beginning of the lecture on section 1.7, linear independence. These notes are posted in Canvas. We start out with this definition. A finite set of vectors, v1, v2 to vp, where p is some positive integer, is said to be linearly independent if the equation x1 v1 plus x2 v2 plus all the way down the line to plus xp vp equals 0 has only the trivial solution, meaning the variables x1, x2 down to xp all equal 0. A set of vectors that is not linearly independent is said to be linearly dependent. If v1, v2 through vp is a linearly dependent set of vectors, then there exist numbers c1, c2 to cp, at least one of which is non-zero, such that c1 v1 plus c2 v2 down the line to cp vp is equal to 0. So the c1, c2, cp can be thought of as a particular solution, so values of x1, x2 to xp. If the only way you can take a linear combination of v1 through vp to get 0 is for each one of these weights to be 0, the vectors are independent. If there's at least one linear combination where one of these weights is non-zero, then we say the vectors are dependent. This idea of linear independence, linear dependence is something we're going to work with all the way through to the end of the course. It's really important. So let's go ahead and look at this exercise here. So this is something we're going to have to be able to do. Determine if this set of vectors is linearly independent or dependent. So I have three R3 vectors given, 1, negative 2, 3, 5, 6, negative 1, 3, 2, 1. So what we want to do is we want to try to solve this equation where we take a variable x1 times the first vector plus a variable x2 times the second plus a variable x3 times the third and get 0, the 0 vector. We want to solve this for x1, x2, x3. If the only solution is x1, x2, x3 are all equal to 0, the vectors are independent. If we can find at least one solution where x1, x2, x3 are not all 0, then the three vectors are linearly dependent. So, of course, what are we going to do? We can take this equation and write it in a matrix form. So we can use our three vectors that were given to begin with and write them as columns, create a matrix A here. The x1, x2, x3 that we're solving for become the entries of this column vector that we multiply by, and then the 0 vector on the right is just the same as this 0 vector, which is like the B in a matrix equation. So what we've done is we've set up a homogeneous system. We're using the language of section 1.5. If the only solution is x1 equals 0, x2 equals 0, x3 equals 0, then the set of vectors is linearly independent. If there are also non-trivial solutions, then the set of vectors is linearly dependent. So let's go ahead and apply row operations to the augmented matrix and solve that system. So I went ahead and I wrote this out ahead of time. I'm not going to talk us through every one or write down every single one of these steps. So I am identifying a pivot in that upper left position, that 1. I'm getting zeros below the 1 through 2 row operations. Then I just notice at this step, I'm not getting a 1 in the second column right away. I just happen to notice here that I have opposite entries in row 2 and row 3. So I'm just going to go right ahead at this stage and add row 2 to row 3. And what that does is that gives me a row of zeros. So if I see that coming, I can just do that at any point. Now I'm going to try to get my pivot position of 1 here in the second column. So I'm going to replace row 2 with 1/16 row 2. And then I think I'm almost to reduced form, but I need to get a 0 up above the 1 in the second column, and that's what this row operation does. And so, again, without having written out all the steps together, I get the row reduced form of the matrix right here. Sorry, pushed it up too high. And of course, we can now translate that into what it's saying about the variables x1, x2, x3. Notice that x3 is a free variable because there's no pivot in the third column. And so we've practiced writing the general solution for this now. Call it the vector x with entries x1, x2, x3. The three entries can be expressed in terms of the free variable. So any solution is equal to x3 times this constant vector, negative a half, 1, where x3 is any real number. Now, what the most important aspect of this is we've found out that we have infinitely many solutions, right? We have non-trivial solutions. We have more than just the trivial solution 0, 0, 0. So what that means about our original problem is that since there are non-trivial solutions to that system, the original set of vectors is linearly dependent. Okay. Comment. If I pick one particular non-trivial solution, and I think what I did here was, the free variable is x3. So I'm going back to my solution. I'm saying if I set x3, if I plug in 2 for x3 and take 2 times each one of the entries here, I get -1, -1, 2. So -1, -1, 2 is one particular non-trivial solution. And I can actually take -1 times the first vector of our set plus -1 times the second vector of our set plus 2 times the third vector of our set. And you can check this out. That's that's the solution. So it's going to add up to 0. The above line is called a linear dependence relation. As long as at least one of those entries is non-zero. In this case, they're all non-zero. And notice that there are infinitely many possible linear dependence relations. It isn't like there's just one possible one. Let's do another exercise. Determine if this set of vectors, so it's kind of same thing all over again. Here I have 1, 0, 0, 1, 1, 0, 1, 1, -1. Is this set of vectors linearly dependent or independent? So once again, I'm going to try to solve x1 times the first plus x2 times the second plus x3 times the third and equals 0, 0, 0, equals a 0 vector. Is there a unique solution? Is there only one solution, which would be 0, 0, 0, right, for x1, x2, x3? Or are there non-trivial solutions? And on the handout, I go right to the augmented matrix. So I hope I'm not jumping too far ahead with that augmented matrix. I can take what I just wrote down here and rewrite this as 1, 0, 0, 1, 1, 0, 1, 1, -1 times x1, x2, x3 equals 0, 0, 0. So here's the matrix form of that equation. And if I think of converting this as representing a system that I can convert to an augmented matrix, here are my first 3 columns of the augmented matrix. And then my 0, 0, 0 vector goes on the right. And I can go ahead and apply row operations to reduce this matrix. I didn't write out all the steps. It doesn't take long. It only takes a couple steps. And I get to this reduced form where, notice, I have a pivot in each one of the first three columns. So for x1, x2, and x3, there are no free variables. Since there are no free variables, there is only the trivial solution, only one solution to that system, x1 equals 0, x2 equals 0, x3 equals 0. So the only possible relationship I can get here is to set each one of those weights, x1, x2, x3, equal to 0. That means the original three vectors are linearly independent. That's our conclusion. Again, I just have an extra comment here where I recopy this equation and say this can only turn, the only solution is when x1, x2, and x3 are all equal to 0. Now, what we've done is summed up at the top of the next page, and I'm going to just read this result and give it to you, and then we're going to reach the end of this video. Suppose A is a matrix with columns A1, A2, AN. So the notation we've been using is we say the matrix A looks like this, right, where the columns are A1, A2 to AN. The columns of A are linearly independent if and only if this homogeneous equation AX equals 0 has only the trivial solution. I mean, that's exactly what we've just done in these two previous examples. So we're not going to write out a proof of this as a separate result, but we're just sort of making this observation. This is an incredibly important result for us that we are going to work with in the future. So I'm going to stop there on this segment. We're going to continue this in the next part of the video for 1.7.